What if we accidentally burn the planet down? But first of all, which planet? Many people will probably think of gas giants right away, like Jupiter. It's a pretty popular question. After all, Jupiter is mostly made of hydrogen, and hydrogen does this. And what if the whole planet burns up like that? Well, overall it's not too complicated, but even this question has some interesting aspects. At the very least, it's obvious that Jupiter hasn't caught fire yet. But what if we really wanted to? Could we actually set it on fire? Interestingly, this idea has already been explored and might even be useful. In fact, there are some proposals of, let's call them practical applications for burning planets. And it's not just about gas giants. A similar question has been asked about Earth. What's more, it actually worried scientists at one point. And I'm not even talking about global warming, but about the possibility of the entire atmosphere and oceans igniting in a massive explosion. So, what would it take to set a planet on fire? Is there any real risk of this happening to us or to other planets in the solar system? And could there be planets in the universe that are much easier to ignite? Why would anyone even want to set planets on fire, and what is stellification? We'll talk about all this and much more today. I'm Andrei, and this is Cosmos Elementary. So what do I actually mean by setting a planet on fire? After all, the word burning can refer to very different processes. When it comes to space, people often casually say that hydrogen burns in the cores of stars, meaning nuclear fusion. But in reality, these processes have nothing to do with the kind of burning we're familiar with in everyday life. This informal use of the word burning when talking about stars can sometimes lead to a bit of confusion. I've come across comments from flat earthers saying something like, "But there is no oxygen in space. How does the sun burn?" I mean, well, today in the context of burning planets, we'll talk about different processes. But let's start with the simplest and most familiar kind of burning we know. That is a chemical reaction involving a fuel, like paper, and an oxidizer, usually oxygen. As a result, heat and light are released. That's what we call fire. Although today we're talking about something a bit different, there is no doubt that in the universe there are planets where, if we landed, we'd burned up pretty quickly. I'm of course talking about planets covered in oceans of lava. Dry wood on Earth starts to burn at about 300 degrees Celsius or about 572 Fahrenheit. But I'm sure many of you already know that there are planets that are much hotter. A well-known example is the planet Corot 7b. It's not a gas giant, it's about 5 times more massive than Earth, and the temperature on its dayside surface can exceed 2000 degrees Celsius or about 3600 Fahrenheit. Lava oceans may be bubbling on its surface. There are at least 2 reasons for this. You've probably heard of exoplanet types like hot Jupiter and super Earth, but Corot 7b has also been called a super Io. This name is by analogy with Io, one of Jupiter's moons, which has hundreds of active volcanoes, volcanic activity driven by tidal forces. The interaction between the Earth and the Moon, and to a lesser extent with the Sun, creates tidal waves in Earth's oceans. There's also an effect on solid rock, but it's much weaker and not as noticeable as the ocean tides. But when a moon orbits close to a giant like Jupiter, the tidal forces are so strong that the moon's interior heats up. The rock melts and active volcanism is sustained. We can see how different is the strength of tidal forces between Earth-Moon and Jupiter-Io pairs. In the case of Corot 7b, it's even more intense, since it's a planet-star system. The planet is very close to its star, and the tidal forces are even stronger. And the second, more obvious factor is that the planet is simply very close to its star, which hits it intensely with its radiation. There are even hotter planets like Kelt 9b, where surface temperatures can exceed 4000 degrees Celsius, or 7200 Fahrenheit. hotter than the surface of some stars. There are no lava oceans there because this planet is a gas giant. Planets can be hot. That's no surprise. But today we're not talking about that. The examples I gave are just the normal state of those planets, caused by their proximity to their stars. It's also true that planets can be hot when they've just formed. Our Earth was likely covered in oceans of lava billions of years ago. Also, a planet can become extremely hot after a collision with a massive body, like the impact Earth is believed to have experienced, which led to the formation of the Moon. Today, however, we're talking about cold and mature planets. Those where, under normal conditions, the whole planet should not resemble an inferno. As I mentioned in the introduction, the discussion about setting planets on fire often centers around Jupiter. And here people often ask questions like, what would happen if you lit a match on Jupiter? And of course, it's easy to see where that question comes from. Think about some substance that burns up really well. What comes to mind? Maybe pure alcohol or gas from a stove? Now imagine a planet where the oceans are made of alcohol and the entire atmosphere is household gas, methane or propane. It would be like having to hang a no smoking sign not just at a gas station but across the entire planet. Well, Jupiter and the other gas planets in our solar system are basically just that kind of planet. Here is Jupiter's atmospheric composition from NASA's website. We see that nearly 90% is molecular hydrogen, H2. And what does hydrogen do? It burns. It's no coincidence I remember the Hindenburg disaster, which was filled with that very flammable hydrogen. Could it really be that if the entire atmosphere is made of a flammable substance, lighting a match in one spot would set the whole planet on fire? What would happen then? Nothing, which is what many of you probably already guessed. If an entire planet made of hydrogen were flammable, it would have burned up long ago. There are lightning storms in Jupiter's atmosphere and asteroids and comets fall into it, burning up as they enter. So there are events way more powerful than a match and still nothing happens. It does not catch fire. Why? So far we've been talking about fairly simple things, and here the answer is simple too. You probably already know it or could have guessed it because I've already explained and showed all the necessary information. Specifically, how combustion reactions work, and what Jupiter's atmosphere is made of. Because besides the fuel, which Jupiter has in abundance, we also need another crucial component, an oxidizer. And usually that's oxygen. Actually, other substances can act as oxidizers too. In rocket fuels, for example, the oxidizer isn't always oxygen. But such substances are much rarer in nature, if they occur at all. Oxygen is actually the third most abundant element in the universe after hydrogen and helium. And free oxygen is practically non-existent on Jupiter. To ignite the entire atmosphere, you'd need a lot of it. There's a thing called the fire window. On Earth, for fire to burn properly, the atmosphere needs a certain oxygen concentration, no less than about 16% and preferably around 18%. But if Earth's atmosphere had more than 35% oxygen, fires would burn up uncontrollably, and fuel would be consumed until nothing was left. Just imagine how much oxygen you'd need, and free oxygen, not oxygen bound in compounds like water or carbon dioxide, to burn all of the Jupiter's atmosphere. Meanwhile, in this breakdown, free oxygen isn't even mentioned. So no, Jupiter, like the other giant planets in our solar system, can't be set on fire with a match, no matter how much fuel it has. By the way, we can also mention Saturn's moon Titan, which has a significant amount of methane in its atmosphere, the very same methane that is used in some kitchens. And it even has entire lakes and seas made of liquid methane and ethane, but none of it catches fire for the same reason. But why is there little to no oxygen on Jupiter, while Earth's atmosphere is rich in it? After all the planets and the Sun originally formed from the same fragment of a gas and dust cloud. So why the difference? Planets followed very different evolutionary paths, and at least on Jupiter there is no life, as far as we know. There are no plants that convert carbon dioxide and release oxygen. And on Earth, when we talk about ordinary combustion, the situation is quite the opposite. It turns out that our atmosphere is rich in oxidizer, about 21% oxygen, but lacks suitable fuel. For example, hydrogen is present at less than 1 part per million. But if you had a planet where hydrogen and oxygen mixed in the atmosphere, say in 2:1 ratio, that would be a much more flammable planet. Of course, there would be nuances depending on conditions like temperature and pressure, but still, it would be much more flammable. And that leads to the next question. In our galaxy alone, there might be 1 trillion planets. Could there be planets among them with fire-prone atmospheres? Well, first of all, we definitely don't know of any like that yet. Although, to be fair, we still know very little about the compositions of exoplanet atmospheres in general. For an atmosphere like that, there would need to be a lot of oxygen. You could think that this would require a pretty big condition like the presence of life, which, if it exists somewhere else, might be very rare. And honestly, we're not sure about that either. But that's not necessarily the case. There could be other mechanisms that enrich atmospheres with oxygen. For example, scientists have studied photocatalytic reactions of water in the presence of titanium oxide. Such a mechanism under certain conditions could even produce an oxygen level in an atmosphere comparable to Earth's. But the question isn't just about oxygen, it's about the right mixture, where the atmosphere contains both fuel and oxidizer in the proper proportions. I haven't found any serious studies or estimates on this topic, so we can just speculate a bit ourselves. And I'd bet that such planets are extremely unlikely. After all, an atmosphere like that would be very unstable. Just one asteroid entering the atmosphere, one lightning strike, and boom. And despite everything I just said, there have been concerns that Earth's atmosphere could catch fire, and not just the atmosphere, but even the oceans. There are also ideas about how to actually ignite a gas giant. But here we're talking about a completely different kind of burning. In the movie Oppenheimer, there's a scene. If you haven't seen it yet, don't worry, this isn't a spoiler, or at least not a major one, where General Leslie Groves discusses with Oppenheimer the possibility that the world's first nuclear test, Trinity, could ignite the entire Earth's atmosphere. Such fears that the explosion of a single nuclear bomb could essentially destroy all life on the planet really did exist. Interestingly, these concerns persisted even decades after the first test. And these worries were not just talk. Here's a declassified document from 1946, a report prepared by the participants of the Manhattan Project. The first paragraph of the introduction reads, "The detonation of a fission or thermonuclear bomb produces a high temperature, which will stimulate the reaction of atomic nuclei of the air with each other. If an ignition point exists and is surpassed, the thermonuclear reaction may be propagated to all parts of the atmosphere." It sounds terrifying, especially coming from an official Manhattan Project report. You might have noticed though that the report is dated 1946, which means it came after the Trinity test. And well, we're still here, aren't we? The real question is for how long? But that report was actually meant to answer whether such a chain reaction in the atmosphere was even possible. Let's rewind a few more years back to 1942. As part of the Manhattan Project, an atomic bomb was developed based on fission reactions. For example, there is a radioactive or unstable uranium-235. If a uranium-235 atom absorbs a neutron, it triggers a chain fission reaction. And when the atom splits in parts, a large amount of energy is released. If you gather enough material in one place, achieve the critical mass, and create the right conditions, you can start a chain fission reaction. That releases an enormous amount of energy. That's how a conventional atomic bomb works. And while it was being developed, one of the Manhattan Project scientists, Edward Teller, was simultaneously working on the hydrogen bomb. At that time, it was hypothesized that the explosion of a small fission bomb could create conditions under which a different type of a nuclear reaction might begin, namely a fusion reaction, where atoms don't split, but rather fused together into new isotopes, releasing even more energy in the process. Yes, these are the very reactions that occur in the cores of our Sun and other stars, and that make life on Earth possible. And thermonuclear bomb was expected to be even more powerful. And Teller wondered, could the entire atmosphere turn into such a thermonuclear bomb, with the atomic bomb acting as the initiator and the whole atmosphere becoming the thermonuclear fuel? Another Manhattan Project scientist, Hans Bethe, recalled that at 1942 meeting, Teller asked whether a fusion reaction could start in Earth's atmosphere between nitrogen atoms, producing oxygen and carbon and releasing an enormous amount of energy. There were even discussions about the possibility that in addition to the atmosphere, the oceans themselves could explode. That would have been a catastrophe of unimaginable scale. There simply would have been no one and nothing left afterward. So the project members did calculations, and by the time of the test, they believed that the chances were, well, in the scene I mentioned from the movie Oppenheimer, they say that the odds were almost zero. Another project participant, Arthur Compton, later said that if the probability of such a catastrophe had been higher than 3 in a million, he wouldn't have continued the project. But calculations showed the probability was a bit lower. Given the possible scale of the disaster, of course, that is not exactly reassuring. Back in the 1940s, though, the public knew nothing about any of these discussions. This all came to light decades later, first in 1959. And then again in 1970s, when some articles were published with recollections from participants and certain documents were declassified. In the 1946 report I mentioned, the scientists came to the following conclusion. Quote, "It is shown that whatever the temperature to which a section of the atmosphere may be heated, no self-propagation chain of nuclear reactions is likely to be started. The energy losses to radiation always overcompensate the gains due to reactions." And although nuclear explosions do create extremely high local temperatures, and even enable fusion reactions in the specially designed part of a thermonuclear bomb, the conditions in Earth's atmosphere are nowhere near sufficient to trigger a reaction across the entire planet. We need not only extremely high temperatures, but also immense pressure conditions that exist in the core of a star, not in Earth's atmosphere. We can also recall how scientists and engineers today struggle to initiate and sustain fusion reactions even in their reactors. And again, consider how many nuclear and thermonuclear explosions have occurred since then, and yet the atmosphere has not detonated. Moreover, this shouldn't happen even if the entire existing nuclear arsenal of all countries were detonated simultaneously. This story is a bit like the fear people had about Large Hadron Collider. More precisely, the fear was that it might create microscopic black holes that could swallow us all. But it didn't, and it can't do that. And even if it did, those black holes would evaporate faster than they could consume anything. There were later articles written when physics had advanced significantly, like this one, that examined whether such a chain reaction could occur in Earth's atmosphere. The authors concluded that even if nitrogen reactions were easier than they actually are, it would still be impossible to ignite the atmosphere under Earth's conditions, no matter how high the explosion temperature. Alright, that's us and now. But what about hypothetical, more advanced civilization? Or maybe us for in the future? Is it even theoretically possible to ignite the entire planet? And more importantly, why would anyone want to? This brings us to the concept of what's known as stellification. What is stellification? You could say it's the process of igniting a planet. The word itself is quite telling. Stellar means relating to a star or stars. Here we're no longer considering Earth-like planets, but focusing on gas giants. Many have probably heard that Jupiter is sometimes called a failed star, but that's not entirely accurate. I covered this topic in detail in my old video about space-related myths. The point is that Jupiter's composition is very similar to the Sun's. Both are mostly hydrogen and helium by mass. But while the Sun is a star, Jupiter is not. And the key difference is that in the Sun's core, continuous thermonuclear fusion reactions take place, which is why it shines. while in Jupiter these reactions do not occur. The whole issue is that Jupiter simply lacks the necessary mass for this. That's why some people say that if Jupiter were more massive, it would become a star, hence the term failed star. But maybe it would still be fair to call it that if it were about 50% less massive than the minimum threshold at which an object can already be called a star. Well, if we were generous, 2 to 3 times less. But in reality, Jupiter is 1000 times less massive than the Sun, and about 80 times less massive than the smallest stars. So for continuous thermonuclear fusion reactions to start in Jupiter's core, like in the star, it wouldn't just need a little extra mass. It would need the equivalent of 79 more Jupiters. So it's really far from being a star, making the label failed star quite misleading. But it seems like our first option, if we just want to fantasize and not limit ourselves by current capabilities, and if we want to ignite Jupiter, we need to simply make it more massive. Massive enough to qualify as a star. But in reality, this option isn't really considered much, even in hypothetical scenarios. Not to say other scenarios are much more realistic, but still. There's another option that brings us back to the previous story. Actually, somehow igniting a thermonuclear chain reaction in an atmosphere. It didn't work with Earth. But Jupiter, after all, is mostly hydrogen, and the pressure there, especially deeper down, is much higher. Maybe if you add enough energy, it could trigger a chain reaction and ignite the whole planet. In the same article I mentioned earlier, which states that this is impossible with Earth, there is a scenario mentioned where, under certain conditions, the impact of a large asteroid could theoretically ignite the atmosphere and trigger a thermonuclear reaction, although such events would be incredibly rare. But there is a much more extravagant idea. How about igniting Jupiter using a microscopic black hole? And this scenario is discussed in that article. First of all, the obvious question, why? Well, maybe you noticed the article's title. It actually contains the answer. Here's the idea. Giant planet systems, with their many moons, are often called miniature solar systems. The problem is that Jupiter, as we've established, can't even be called a failed star. Plus, it's far enough from the Sun that no matter how many moons it has, none of their surfaces have conditions suitable for life. Maybe beneath Europa's eyes, but building a base there doesn't really seem like a great idea to us. Mars is probably a better choice. But if you turn Jupiter into a star or star-like object, that changes things. That way you could terraform some of Jupiter's Galilean moons. Ignited Jupiter could warm Europa and Ganymede, melting their icy crusts. In theory, gases could be released in the process, creating an atmosphere and much more favorable conditions for life. In this paper, the author Martin Fogg writes that in theory such an event could create Earth-like temperatures on Europa's surface and Mars-like temperatures on Ganymede. But still, how to actually do it? Considering that black holes are involved here, along with manipulating them, it's clear that the scenario is very speculative and requires several assumptions. But the question here isn't whether we can do it. Obviously we can't. It's more about whether it's possible in principle, and that's not so clear-cut. The paper's author suggests inserting a microscopic primordial black hole into Jupiter. And the first assumption we need to make is that primordial black holes even exist, something we don't know yet. In reality, we have little doubt about the existence of supermassive and stellar black holes. But with primordial black holes, it's much more uncertain. There is a theory that soon after the beginning of the universe, a large number of black holes could have formed without formation of stars. Matter might have collapsed directly into them. Interestingly, it's believed that such black holes could have had a wide range of masses, from thousands of solar masses down to very tiny ones. In this case, it's proposed to find a primordial black hole with a mass of 10 to the power of -4 Earth masses. That's approximately 6 times 10 to the power of 20 kilograms, or just under half the mass of Earth's global oceans, or about 0.63 the mass of the dwarf planet Ceres. We know that black holes are compact objects, and at such small mass, the radius of this black hole would be only about 887 nanometers. To put it roughly, that's about 100 times thinner than a human hair. I'm talking about a microscopic black hole. So not only do we have to accept that they exist, but it'd also be great if one happened to be nearby. So far we haven't found any, not just nearby, but anywhere at all. However, the paper estimates that depending on certain parameters, the closest such black hole could be located somewhere around the Oort cloud or even near Pluto. By the way, this reminds me of one story. There is a hypothesis that unusual behavior of objects in the Kuiper belt is caused not by a yet undiscovered ninth planet, but rather by a primordial black hole with a mass of several Earths and the size of a grapefruit. So scientists do occasionally toy with ideas like this. But for now, we're just speculating. So first, this black hole has to exist. Second, we need to be able to detect it. And then it has to somehow be transported to Jupiter. One proposed idea is to use an asteroid as a sort of a tow truck or a tug. Place an asteroid in orbit around such a black hole. Then, at certain moments, artificially give the asteroid a push, say by installing some kind of engine on it to gradually change the trajectory of the entire black hole asteroid system and slowly tow it closer to Jupiter. What's next? Next, you need to place a black hole inside Jupiter. First, you put the black hole into an orbit close to Jupiter so that it passes through the planet's atmosphere. Gradually, it will lose orbital energy and essentially spiral down into Jupiter. This process might be accompanied by powerful bursts of energy, and ultimately you want the black hole to remain entirely inside the planet. The closer to the core, the better. Once the black hole is fully inside Jupiter, constant accretion will begin. The big question, of course, is how to stabilize the black hole inside the planet and keep it fixed in the right place or orbit. It's no secret that detecting a black hole can be quite difficult, especially if it's isolated from other objects and lacks surrounding matter to reveal its presence. We usually detect them by indirect signs, for example, when a black hole accretes gas from surrounding space or a companion object. The matter heats up to extremely high temperatures, many times hotter than the surface of stars. So here it's exactly this process that would heat up and make Jupiter shine. The black hole inside the planet accretes gas and heats it up, producing heat and light. At the same time, a certain equilibrium could be established between the rate of matter absorption and the pressure exerted by the radiation produced in this process. This results in a kind of gravitational device inside the planet that turns it into a star-like object. So in theory, such a system could remain stable for quite a long time. The paper suggests that under certain conditions, Jupiter's moon could have life-supporting environments for a period ranging from 10 to 100 million years. After that, it would be best to surround the planet with a mini Dyson sphere. Then, somewhere around 500 million years later, the planet would need to be dismantled so it doesn't become too bright. All of this, of course, sounds more like science fiction, but at least some of the processes we've described here do exist, and it's possible to imagine that a highly advanced civilization could accomplish something like this. Maybe they wouldn't even need to search for a suitable black hole, they might create one themselves. Speaking of highly advanced civilizations, I've come across the idea of considering stellification when searching for technosignatures or signals from other advanced civilizations. Add this to the list alongside artificial signals and the search for megastructures like Dyson spheres. Also include stellified gas giants or brown dwarfs, which might have their own unique signatures. If we're not capable of this, maybe someone else is, and it could help us find them. In short, once again, I'm convinced that behind the simple question, is it possible to ignite a planet, there can be many interesting and far from obvious stories. Thanks for watching. Links to all of the sources are, as always, down below in the description, and if you enjoyed this video, feel free to check out my other videos and subscribe for more videos in future. Bye.